Hello guys, welcome back to KD Code. In this video, we are going to discuss about bit manipulation and the related DSA questions. Let's start with the basics of bit manipulation. So, what are the bits? In computer, we know that numbers, characters, program, everything will be stored in the form of bits, right? So, let's see basic numbers, how they are represented in the form of bits, right? Let's start with the numbers. So, for number 0 here, it will be stored in the form of 32 bits. Okay, let's take 32 bits. Okay, so in the 32 bits format, 0 will be stored in the form 0 0 0 0 0 and so on. So there will be 32 bits of zeros, right? So 1 will be stored in the form of 1 0 0 0 and so on. This is also 32 bits. So how to get this binary number? It's so simple. So the first binary bit, that is the least significant bit, we call it as least significant bit from right side, and from left side we call it most significant bit. So the least significant bit is nothing but it has lower value contributing to the number, right? So let's take 10 here. So then bits will be represented in form of 2 powers, right? So first one will be 2 power 0, second one 2 power 1, third one 2 square, 2 cube, 2 power 4 and so on. It will be until 2 power 31. These are 32 bits, right? So for 10, what we have to do? So you calculate it, 1, 2, here it is 4, 8, 16 and so on, like this, right? Let's represent this 10 in the form of these bits, right? So we cannot take 16 because 16 is greater than 10, right? So we take 8 because 8 is less than 10, and let's say 10 minus 8 is equal to 2, right? So we need 2 again. So we cannot take 4 because 2 is lesser than 4, and we can take 2 here again, right? So 2 minus 2 equal to 0. So we don't need anything else, we can put 0 everywhere. So this is the binary system number for 10, right? This is the binary number for 10, right? So for 10 it is, we can simply represent it in the 4 bits, like 1 0 1 0, like this. So for 9 it will be, calculate here, 8 and 1, right? So it will be 1 0 0 1. The same way for all numbers, we will be representing it in the form of a binary system. In bit manipulation, this is so important. This is very basic actually. So if someone doesn't know it, please practice few numbers. So for 0 1 2 3 4 5, it will be very easy. You can write it like this: 4 2 1 0 0 0. For 1 it is 0 0 1. For 2 it is 0 1 0. For 3 it is 0 1 1. And for 1 0 0 1 0 1. And for 6 it is 1 1 0, and for 7 it is 1 1 1. So simple, right guys? You can also see some pattern here. For 0 it is all zeros, for 1 it is 1 here, and for 2 it is here, and for 3 it is 2 ones again, right? And for 4 it is 1 again, 5 it is 2 ones, and 6 is 2 ones. So we'll find some pattern here in the coming problems also. I will explain that in the problem. It will be more clear, right? Let's get into the next basic things we need to learn. The next thing we need to learn is get the 8th bit. So what is this get the 8th bit? It's nothing but, let's say if for 10 it is 1 0 1 0, right? So this is 0th bit, first, second, third. These are the position, right? So what if I want to get the first position? That is the first position, this position bit. I want to know the value of this bit. Okay, how can I do it? So before knowing how to do it, we need to learn about the shift operators. Yes, the shift operators. Shift operators. Well, so there are only 2 shift operators, the left shift and the right shift. So what does this shift operators does? It's very simple, guys. So the left shift operator, basically what it does is it will shift the bits to the left, right? So for 1 0 1 0, if I want to shift the bits by 1 position, then these things will be shifted 1 position to the left, right? Like this, 1 0 1 0, and this will be 0. Okay. And what if we use the right shift operator? The same thing, guys. If 1 0 1 0 I use this, all the bits will be shifted to right in the position of 1. If I want to shift it by 1 position, it will get shifted to 1 position, right? Like 0 will be shifted to, that is not present here, so this is void. So 0 will be gone because there is nothing in front of 0, right? Because this is the first position, right? So 1 comes here again. 1, 0, 1. So 0. This becomes like this, right? So whatever the number you mention, it will be shifting the bits that many times. Okay. So for example, this operation can be represented as 10 left shift operator and 1, right? This can be represented as 10 right shift operator of 1, right? This is how we do it. So if you represent it by 2 here, 10 left shift of 2, what happens? Yes, you get it right. 1 0 1 0, it will be shifted 2 times of this position to the left. It will be shifted to left 2 times. So 1 0 1 0, these 2 positions will be 0 0. So this is how left shift operator works, right guys? So the next operators we need to learn are AND operator, AND operator, right? So what is this AND operator? It will be represented by this symbol AND. So what it does is, if I take 10 1 0 1 0, and if I take some other number like 9 1 0 0 1, so what it does is, if the 2 bits in the same position is 1, then the output will be 1. If any one bit is 0, this or this, it will be 0. So simply saying, the output of AND operator is 1 if both the operands are 1. Right guys? So for 1 0 1 0 and 1 0 0 1, this is 0, this is 0 0, and these two are 1, right? So it is 1 here. The output is 8. So that's how AND operator works, guys, right? Now let's talk about OR operator, right? So OR operator is very simple as AND operator. OR is represented by this symbol, and if I take 10 again, 1 0 1 0, and 9 again, 1 0 0 1, OR operator, what it does is, if any one value is true, output will be true. Yes, you had it right, guys. Or you can say, if both values are false, then only it will be false. If any one of the value is true or true is true. Okay guys, so that makes sense. OR operator, so 0 or 1, it is 1 because we have at least one, right? 1 or 0, 1, 0 or 0, it is 0 obviously. 1 or 1, so 1 or 1, we have 2 ones, at least one we are needed, right? So 1, so it is 11. So now there is one more operator we need to learn, that is XOR operator. This is very important, guys. We will be using this operator in the many problems, right? So listen carefully. For the XOR operator, what we have to do? It's very simple, guys. Again, for AND, if both are true, then only it will be true. For OR, if both are false, then only it will be false. Okay? Left shift, right shift operator, both are clear, right? So coming to XOR, it is very simple, guys. If both operands are same, output will be 0. So like 1 1, it will be 0, 0 0, it will be 0, 1 0, it will be 1, 0 1, it will be 1 again, right guys? So if both the operands are 0, then it will be 0, else it will be 1. This is a simple XOR operator, right guys? Now using this XOR operator, we can tell one thing. What if I XOR the same number with itself? What happens? Yes, you guessed it right. I guess you guessed it 0, right? Because you see 1 0 1 0 and XOR of 1 0 1 0, what happens? Everything is same, right? So for same, it will be 0 0 0 0 0. So output will be 0. Not only 10, any number, it will be 0. So same number XORing with itself is always 0, because the same numbers, right guys? For same, it will be 0. Now coming back to getting the ith bit for this number. Now let's see, how do you get the ith bit? So using the shift operator, we can do this. shift operator, right? Not only using the shift operator, we have to use the AND operator also. So how do we do this? So for 10, it is 1010. I want to get the second bit. I want the second bit. This is the first bit. This is the second bit. So how do you get this bit? How do you actually get this bit? So shift this number by right one time. Right? You shift it by one time. What happens? It becomes 101. So you know this bit is the second bit now. Right? Now what you have to do simply is you have to do AND with number 1. Right? 1 is nothing but 001. Right? So it gives the output. These things will be 0 every time, because we know for 1 all left portion will be 0, right? This is the only one bit we need. So we will do an AND operation here. So it will be 1. So the output is 1. I know for the second portion it is 1, right? So simple, guys. So what you have to do, if number is equal to 10, what we have to do? We have to do number, we need the position of 2, right? So what we have to do? We have to do like this. We have to right shift it by 1, because we need position 2, right? We only shifted it one time here, right? So we need to right shift it by one time. So there is nothing but position minus 1, and we have to do an AND operator here with 1. So if you don't want to do it like this, there is one more way. So instead of manipulating our given number, you can take 1. For example, 1010, it is there, right? So you need 1, 2, second bit, right? This bit. So what you have to do? You take 1, 0001. This is the 1, right? So you left shift it by 1. So it becomes like this, 1010 and 0010, like this, right? So our 1 is at second position. This is where I need the bit from the original number, right? So you do an AND operator here. It will be 0 again. 0, 0. So based on this, it will be 0 or 1, right? It will be 1. I know the speed is 1, right? So what we are doing it here? It's simple, guys. Remember, we are doing AND operator with 1. We are left shifting this 1 with position minus 1, right? So this is a formula for getting 8th bit. Right? Now what if I want to set the bit, right? So what is this set the bit? It is quite opposite to get the bit. We're getting the bit when I say get the bit, 8th bit. Now here setting the 8th bit is nothing but, if it is 0, we have to convert it to 1. That's it. If it is 1, we do not do anything. Yes, also we can convert 1 to 1. Nothing changes. Right, so how do we do this? So for 10, it is 1010, right, guys? So if I want to convert the second position, okay, let's say if I want to convert the third position to 1, that is setting the third position, right, guys? Setting the third position. How do we do it? So we take 0, 0, 0, 1, it is 1 again. We need to set the third bit, right? So we left shift this 1 by 2 positions, right? Position minus 1 again, right? So it will go to the third position, 0, 1, 0, 0. Now think about it. How do we convert this to 1? Yeah, you guessed it right. It is OR operator. This operator, right? So 0, 0, 0, 1, 0, 1, 0, 1. Now it is converted to 1, 1, 0, it's 1. So without changing other bits, we just set the third bit to 1. Right, guys? So the formula is number or 1 left shift position minus 1. This is very simple, guys. Set 8th bit. Got it, right? Now to learn here is clear the 8th bit. So here we got the 8th bit. Here we set the 8th bit. So what is clear the 8th bit? It's very simple, guys. Again, you need to convert 1 to 0. It's opposite here. Yeah. So if there is 10, 1 0 1 0, I need to clear the second position. Then I need to convert this 1 to 0. So how do you do it? It's very easy. Take 10, 1 0 1 0. Now you know 1 0 0 0 0 1, right? This is 1. Now you need to convert this second position. That is, you need to clear the second position. That means converting it to 0, right? So first of all, we need to take this 1 to that position. So left shift by position minus 1 again. So we take this 1 to the second position first. Then we'll think about it. So 1 0 1 0 0 0 1 0. So we took it here, right? We took it to the second position. Now what? We need to convert these to 0, right? And we should not interfere with other positions. It should be same. What we have to do? Come on, think. Can we use XOR? No, guys, because XOR takes same elements and it will convert to 0, right? But here also there are same elements. In this case, it might work. But what if I want to clear the third bit here? Third bit 1 0 1 0 1 0 1 0 0, right? If I use XOR, you see here it is 0, here it is 1, but here it is 1 again. But I need to convert it to 0, not 1, right? So XOR doesn't work here, guys. So to clear XOR doesn't work. What do you have to do then? So you need to learn one more thing here, that is one's complement. One's complement. What is it? It is nothing but toggle all the bits, right? You had it right. So 0 0 1 0, you have to toggle all the bits. Convert 0 to 1, 0 to 1, 1 to 0, 0 to 1, right? So after converting, it will be like this, 1 1 0 1. Now you apply the AND operator here. So all ones will not change the other bits. So 1 0 1, 0, right? Now this bit is 0. So whatever you do, this will be 0 again. So I am setting that bit to 0 and I am not touching the other bits because all other bits are 1, right? So what we have to do it here? What is the formula? So we did left shift this 1 by position minus 1, and we did then 1's complement to this number, that is 1, right? After shifting it left position minus 1 times, right? And we did an AND operator with our number, right? So this is a formula to clear the ith bit. Clear ith bit, right? So this is the formula to clear the ith bit. So there is one more formula you need to learn. That is toggle ith bit. So what is this toggle? What you have to do? It's very simple again. Then you have to take 1 0 1 0. You have to convert the second bit. Maybe you toggle the second bit. Okay. How do you do it? If it is 1, convert it to 0. If it is 0, convert it to 1. This is what toggles mean, right? So the second position 1 0 0 0. This is how it looks after you toggle the second bit, right? Let's see how we can do it. Now again, take 1 here, 0 0 0 1, right? You need to do something to the second position, right? Take it to the second position again, position minus 1, right? So 1 0 1 0 0 0 1 0. You came to the second position. What you have to do basically? You need to convert 1 to 0 and 0 to 1. So let's think. Here all other things are 0, right? So what if I use XOR operator? So XOR operator, what it does? XOR operator basically, if it is same, it converts to 0. If it is different, it will convert to 1, right? So I have 0 here. What if the original number has 0? It is same, right? So it will be 0. And what if the original number has 1? What happens? It will convert to 1, right? So it doesn't change the original number here. the output, right? What if it is 1 here, 1, and original number is 0? What it does? It is different, right? So it will convert to 1. What if it is 1? It is same, so it will convert to 0. So you toggle the bits. For 1, for 0 it will be same. So I just do an XOR operator here. It will be 0, 0, 0, and 1, right? That is what I need here, right? So what is the formula then? We took a 1 to the position -1. We did an XOR operator with this number, right? This is the formula. Okay, these two triple ith bit. So let me take all the formulas into one place. So you see, I placed all the formulas in one place. You can have a closer look. To get the ith bit, we use 1. We send that 1 to the position -1, and then we use AND operator here, right? And same thing goes for setting the ith bit. So we send our 1 to the position, and we use OR operator. And for clearing the ith bit, we send our 1 again to that position, and we convert that 1 after sending that 1 to that position. We take the 1's complement. We toggle all 1's to 0 and 0's to 1, and we do an AND operator with our number, right? That is how we clear the ith bit. And to toggle the ith bit, we just again take the XOR operator after sending our 1 to the position -1, right? This is how it works. So this is the 1, 2, 3, 4 formulas you need to remember every time, because these are important to spontaneously do the problems. Now let's get into the DSA related problems one by one. Right, guys? Now let's talk about the first problem. What is it? Count the number of bits. 1 bits. Okay? Count the number of 1 bits. So you just have to count the number of 1 bits in the number, right? For example, for 10 it is 1010. We have two number of 1 bits. For 9 it is 1001. It is 2 again, right? So how do we count it? Yeah, just have a pause of the video and think about it. Now after you're thinking, coming back, let me tell you the solution. It's very simple, easy problem. So just iterate through this number. How do you iterate through a number which is a single digit number, right? How do you iterate it? Yeah, we use shift operators, right? These are the shift operators, right? So we use shift operators, precisely the right shift operator. That's how we take the least significant bit every time by using the AND operator again, right? For example, 1010. I take 0001 and do AND. What happens? I'll get the 0th bit, right? It is 0. I got 1 bit. Right shift. What happens? 101 shifts 1 bit right side, right? And again I do AND operator with 1. What I get? 1, right? It's 1. I got the first bit. So basically it is 0, but the original number, it is the first index bit, right? So that's what I'm talking about. So this is the 0th bit, this is the first bit, and second bit, third bit. Until then the number becomes 0, right? So if I do this again and again until the number becomes 0, right? So it converts to. So after right shifting again one step, it will be converted to this number. I'll do take the least significant bit again, it is 0, right? And after that I'll convert again. It will be like this, and this is 1, and after shifting one more time it will become 0 completely, right? So this is my stopping point. Stop. So basically I'm iterating through every element, every bit in the number, right? So I can use while loop, right? So until while, if n equal to 10 here, n is not equal to 0. I can iterate until n is not equal to 0, right? And I define a count variable to count the number of ones, right? So think about it. The output will be either 0 or 1, 0 or 1, right? So I don't need to put an if condition here. Instead, I just add those numbers of the output to the count. If it is 0, it will add 0. If it is 1, it just add 1, right? So count plus is equal to n and 1, right? This is how we get the loss significant bit value for this number. And what do? In the next step, we have to shift it to right by one step, right? We can do it using right shift operator like this, right? I send it back to n again. So this is the code to get the count of 1 bits in a number, right? The time complexity will be O of what? Do you think it is n? No, it is not n. Think about it. At least 10 times I am not traversing this while loop, right? I just traverse it 4 times. So what is it? So it is nothing but log of n. So for example, log of 10. I can write it as log of 2 power 3, right? So 3 log 2, 3 point something. So that many times I am just iterating this, right? 4 times. So I'm iterating over only 4 times, right? So I can say I'm iterating log n times, right? For example, if I take 16, it will be 16, 8, 4, 2, 1, 1, 0, 0, 0, 0, right? Log 16 is nothing but 2 power 4. That is 4. So I'm iterating only 4 times to count the number of ones, right? That is how I log n. And the space complexity is O of 1 because I'm just using one variable, that's it. I'm not using any arrays. So going to the second problem. What is our second problem? You have to check if the ith bit is set or not. So how do you check a bit is set or not? It's very simple, right? We get the bit, get ith bit. If it is 1, it is set. If it is 0, not set, right? We know how to get the ith bit. How it is? Number and 1 left shift by I minus 1, right? This is nothing but the position of the bit we need. So if this is 1, then it is set bit. If it is 0, then it is not set bit, right? You can just return it. Return, right? Equal to 1. So we'll return the true or false here, right? That's so simple. And the time complexity, it is, I would say it is O of 1. Space complexity, it is O of 1, right? It's very easy problems, right? Let me take third problem here. It's nothing but you have to find if the number is even or odd. So how do you find if your number is odd or even? Let's analyze the even numbers and odd numbers. Let's take the couple of even numbers 2, 4, 6 and odd numbers 1, 3, 5. So for 1, if I convert it into the binary system, 0, 0, 0, 1, and for 3 it is 0, 0, 1, 0, and for 5 it is 0, 1, 0, 1, right? For 2 it is 0, 0, 1, 0. For 4 it is 0, 1, 0, 0. For 6 it is 0, 1, 1, 0, right? 8, 4, 2, 1. If you want to get the binary system clearly, you just write 8, 4, 2, 1 and convert the numbers into their binary system, right? It will be easier. So now if you observe one thing, the even numbers here has 0 in the first bit. I mean the 0th index position, the first position or 0th index position, there are zeros, right? And for this is 1 here, and for odd numbers it is 1. for the first position or 0th index, these are ones. So I just have to find the first position is 1 or 0. If it is 1, I would say it is odd. If it is 0, I would say it is even. That's it. That's it, guys. So is even, write a function is even, return, I'll get the first position, right? So it's nothing but I just do it with 1, the AND operator, right? So even, it should be 0, equal to 0. That is even. If you want to write the odd function, same thing I can copy paste. Yeah. Same thing I can copy paste, but I need to change this. I can do like this, 0 equal to 1. I'll just return it like this. Yeah, these are two functions I can write. The time complexity will be big O of 1. Space complexity will be big O of 1. Right? This is also a simple problem. Now let's go to the next problem. Fourth problem. That is bit difference. Bit difference. You need to find the position of the first different bit. So what I'm saying here is, let's take 10 here. 10. It is 1010, and you take maybe 4. It is 0100. The first bit is same, right? So you go to the next bit. It is different. So you return the second position as your output. That's it. Right? How do you compare it? So you just have to iterate through all positions in both numbers at the same time. So how long you have to traverse it? Until 32 bits, right? So what can I do is, I equal to 0, right? If I want to get the first one, what I will do? Number and I minus 1, right? So I is nothing but position. So instead of 0, I take it from 1. And in the while loop, if I is like less than 32, so I can go until 31, right? Less than or equal to 32, because the number and 31 is nothing but the lost bit, most significant bit, that is the lost bit, right? So I can go until 32. So this is nothing but I minus 1, right? So 32 minus 1 is 31. So I can go until 32. From 1, right? So what do you have to check? I have to check if I'll say number 1 equal to 10, number 2 equal to 4, right? Like this. I can define it like this. Now if number 1 and I minus 1, so instead of I minus 1, maybe I can take I only and start from 0. That would be fine, I guess. Less than 32, right? So it will go from 0 to 31 again. That's fine. So instead of I minus 1, I can simply say I. If both are equal, okay, instead I'll say if both are not equal. If both are not equal, I'll return that position value, right? I plus 1. I need to return the position or the index. Okay. So if there are no differences, I can say minus 1, return minus 1. There is no position that having difference, right? It's again the time complexity is log of n. Space complexity is big O of 1. Going to the next problem, 5. The fifth problem is non-repeating numbers. Non-repeating numbers. So what are these non-repeating numbers? So for example, I will take one example. 1, 2, 3, 2, 1, 4. Right? These are some numbers. This will be given as an array. Right? If you observe here, 1 is repeated, 2 is repeated, 1, 3 and 4 is not repeated. So our output will be 3, 4. You got it, right? So how do you find 3 and 4 here? That is the question. So if you remember the things we learned here in the first page, so we have learned something about XOR operator. What XOR operator does? If it is same number, it will be 0, right? So what happens if I XOR all the numbers here? 1 XOR 2, XOR 3, XOR 2, XOR 1, XOR 4. So this one will cancel out and become 0. This two and cancel out become 0. So what happens if you do XOR of 0 with some other number, like 2, maybe here? What happens? 0, 0, 0, 0, 0, 0, 1, 0. So you don't know. Let me tell you. It will be the same number. It will be the same number as 2. So if you XOR with 0, it will be same number. Right? These two are same, 0. These two are different, 1. Same, 0, 0. Right? It will be the same number. And one more property for XOR, right? You have to remember here. Right? Remember it. So at last, I will get the XOR of two different or XOR of two unique numbers. Okay, two numbers we have to find out, right? There will be only the two numbers, non-repeating numbers, only two. Okay, this is the question, actual question, right? So I will get the 3 XOR 4. So what is 3 XOR 4? Let's see. 3 is nothing but 8421 00 10. Sorry, 00 11. And 4 is nothing but 01 00. Right? Let's XOR it. What is XOR? 1 1 1 0. It is same 0. Right? What is this? It is nothing but 7. Right? 3 XOR 4 is 7. So if you carefully observe what we have to do, there is one more property maybe you have to learn it here, which is getting the rightmost different bit from this XOR, right? So if I do like this, XOR is nothing but the 7 value is 0 1 1 1, right? 8421, right? If I take the negative value for 7, it will be 2's complement. 2's complement. It's nothing but 1's complement plus 1. So the negative number is nothing but the 2's complement. How do we calculate it? As 1's complement is nothing but 0 1 1 1, we convert it into the 1's complement 1 0 0 0, right? We add 1's complement 1. This is nothing but the 2's complement, right? So we add 1. What happens? 1 0 0 1. So this is the 2's complement for 7. We take 1 0 0 1. This is the 2's complement. Nothing but minus 7. Okay. We do AND operator here. Okay. Listen carefully. We do AND operator. What happens? This 1 0 0 and 0. Right. So we got 1 here. What does this mean? So what does this mean is the two numbers 3 and 4 differ by first position. The rightmost bit is the first position, right? So 3 is 0 0 1 1, 4 is 0 1 0 0. So if you see the first bit, where it differs first time, right? From the rightmost bit to the least significant bit, the first bit to differ is position 1, right? That is what we need. We don't know about 3 and 4, right? It differs at first position. We know that. It will be 1, either 0, right? Right? Yes. So I take the numbers 1, 2, 3, 2, 1, 4, right? Now what I will do is, let's take two numbers, x and y. I will take both as 0. Now I will take the first position of this XOR, that is 7, right? And I will check the first position of all other numbers, right? So if the first position of some number is 1, I will send it to one list. If it is 0, I will send it to another list. List in the sense I just XOR with this x and y value. So let's take it is 1, it is 0. For 1, what is the value of first? 0 0 0 1. The first position is 1. So XOR with x. And for 2, what is the XOR? What is the first position for 2? it is 0, right? So I'll solve it y. And for 3, what is 3? 0, 0, 1 is 1, right? It is 1, so I'll solve it x. And for 2, again it is 2 here, and 1, again it is 1 here, and 4, what is 4? 0, 1, 0, 0, right? It is 0, so 0, it goes here, right? So now if you observe, what happens? 1, 1 cancel out, 2, 2 cancels out, 0 is or 3 is nothing but 3, 0 is or 4 is nothing but 4. So x is 3, y is 4, and finally we got the unique numbers. So if you didn't understand this, go forward and watch it again. So what you're basically doing is very simple. You find the XOR of all numbers. XOR of all numbers. You find the XOR of all numbers, right? The second step is to get the rightmost different bits position, right? This is the position where it differs. The formula for this, you know this, right? So you get the number, you do an AND operator with its negative number. So this is a 2 complement. Just don't need to manually do the 2 complement. Just do like this, it will be converted into the 2 complement programmatically inside. You don't need to do it manually, right? You can do like this. It will give the rightmost different bit position, right? Now what we have to do? Assign x equals 0, y equal to 0, then iterate over numbers and do XOR with x or y based on the rightmost bit value, right? If it is 1, you can go with x. If it is 0, you can go with y, right? At last, x and y will contain the unique elements, unique values, right? Return them. So simple. Let's write code for it in C++. I'm taking an integer, unique XOR equal to 0. I'll take the for loop. Int I equal to 0, I is less than n. So n is nothing but array dot len dot size in C++ and I++. So I'll do XOR with all elements, right? So XOR equal to array of I, right? So this will be having all the XOR values. Now what? The second step. This is the first step is completed. Now the second step. What is the second step? Rightmost different bits position. So how do we do it? We'll take integer value, right? Most bit position equal to, this is the XOR value, right? So unique XOR and of minus unique XOR. This is how we get the rightmost bit position value, right? Now x equals 0, y equal to 0. Int x equals to 0, y equal to 0. Now iterate over numbers. So again, for loop, we can copy this again, paste it here. So iterate through all the numbers. If that number position, there's the rightmost position, right? Most bit position. If it is not 0, it will be 1 or some other number, right? So then I will assign it to x. XOR array of y, right? Else it goes to y, right? Now return x and y, x comma y. So this is how it is. Very simple. Now coming back to time complexity, this is big O of n, right? This is a big O of 1 and this is big O of n. So the time complexity will be totally big O of 2n, right? Space complexity will be big O of 1 we are using only the variables, right? So that's how we do this fifth problem, non-repeating numbers. This is an important problem. Just now the next problem is the sixth problem. Sixth problem. What is sixth problem? It is to check if a number is power of 2 or not. So how do you check a number is power of 2 or not? So let me give some examples. For 16, it is 2 power 4. It is power of 2, right? For 8, it is 2 power 3. For 4, it is 2 square. And for 32, it is 2 power 5, right? And for 28, it is not a 2 power, right? It is not a 2 power number. So for 1, yes, it is 2 power 0 is 1, right? So how do you find this? It is very simple, guys. Again, you just have to count number of ones bit. The ones bit should be only 1. The count should be only 1. How? Let's see. 2 power 0, 2 power 1, 2 square, 2 cube, 2 power 4, 2 power 5, and so on. 2 power 32, right? So for 1, it is 2 power 0, right? It will be 1 here. And for 2, it will be 2 power 1. And it will be 1, 0, 0, and so on, right? And for 2, 2 power 2, it will be here. What is this? This is 4, right? This is 2, this is 1, and it will be 8, right? So if you observe all these 2 power numbers, they had only one bit set, right? So you just have to count the number of ones. If it is greater than 1, you just return false, as is true, right? So you take a while loop. You just copy the same count number of ones. Copy, paste it here, right? Now what we have to do? Things we need to do here is put a small while if condition inside this while, right? If count is greater than 1, return false. At last you return true, right? That's how it works. So the time complexity will be O of 1. Sorry, we go of log n. Space complexity will be big O of 1. Space complexity will be big O of 1. Now let's go to the 7th problem. That is, count the set bits, right? So for 10, it is 1010. But the trick here is you have to count the set bits from 1 to the given number n. Is n, right? So for 1, it is 1. For 2, it is 2. For 3, for 2 it is 1. For 3 it is 2. And so on. You have to count until 10, that is 2. You have to sum up all this and return the value. So the brute force. So the brute force would be iterating through all the numbers using a for loop I equal to 1 to n, iterating all the numbers. Call this count number of bits, right? Count bits of I. Here to sum up all those, right? So sum equal to 0. Sum plus equal to count number of bits. This will return the number of bits for each number and return sum, right? So what is the time complexity here? The time complexity will be big O of n, and for finding the count bits, log n. And space complexity is O of 1. But the problem asks us to find the number of bits in only log n time. Yes, you had it right, only in log n time. Can you think of any solution to find the number of set bits in log n time? That's why it is a hard problem, not an easy problem. at least for me, maybe. So coming back here, let's say, let me explain this. Let's say the n is 16, right? What you will do? Let's take 16, 8, 4, 2, 1, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so on, right? So for 0 it is 0, for 1 it is 0, 0, 0, 0, 1, and for 2 it is 0, 0, 0, 1, 0. Let me do this quickly. 0, 0, 1, 0, 0, 0, 0. So if you see, can you observe this? There will be a pattern here. So I said it right already. There will be pattern here also, right? This is a problem where I want to explain you what is a pattern. So if you observe the first position, right? You see it will be 0, 1, 0, 1, 0, 1. So it will be every time 0, 1 only, again and again. For the consecutive numbers, every time. And for second position, that is 2, right? You see 0, 0, 1, 1. This repeats every time. 0, 0, 1, 1. 0, 0, 1, 1. Right? And for third position, that is 4. If you check it, it repeats 0, 0, 0, 0, 1, 1, 1, 1. 4 times. Right? And so on, like this. Again. For 8th position, if you see, it will be repeating 8 zeros first. Right? And then 8 ones. For 16 also, it will be 16 zeros first. Right? So that's how it works. If you manage to find the number of ones according to the position, instead of the numbers, it will be easier. You can find the time complexity of big O of n, right? So let's take an example. Let me take n equal to 17 and position equal to 3, right? So for position 3, it is 4 here, right? So let's take k equal to 4, right? Now let's write it. The k series, let's write it until 17, right? So it will be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, right? So for each number, I have to write the position 3, that is k equal to 4 bit position numbers. So what we have to write? It's very simple. K equal to 4 in the sense, it will be 4 zeros every time, 4 ones every time, 4 zeros every time, 4 ones every time, and that's it. Until 17 we count it, right? Now let's see. You see, it's 4 zeros, 4 ones, 4 zeros, 4 ones, and then 2 zeros. That's it. So maybe I can tell this is the first group, second group, third group, fourth group, right? First one, second one, third one, fourth one. You see the even numbers is 1. Odd numbers it is 0, right? So now what I'm going to do is, let's take 17 and I do 17 divided by k. Nothing but n by k. What is 17 divided by 4? You know it is 4. You take the C value, right? So you got 4 groups here, right? 4 groups. Now if you further divide 4 by 2, because only 2 groups is fully ones, right? So it will be 2. Now I have 2 groups with all 4 ones, right? So 2 into 4 is 8. So 8 set bits for 2 groups. But this isn't over. I need to count here also, right? There might be case this is even and I just left it without counting, right? So I have to count it anyways. For example, if n equal to 13, right? N equal to 13 or 12, maybe 12 until here, right? Until here, I will do like this: 12 divided by 4. What is it? So for n equal to 12, 12 divided by 4 is 3, right? So I got 3 groups here, 1, 2, 3, and I just left with 1 here. Let's see about it. So I got 3 groups, right? I have to get the 3 by 2 because half of them will be zeros. So 3 by 2 is 1. I got only one group with all ones. 1 into 4 is 4. 4 set bits. These are the 4 set bits here, right? But I just have one here which is left out. How to find this? So you can find it like this. To take the remainder for 12 when you divide it by 4, right? It is 0, right? So instead what you can do is, maybe let's do like this. When you take 12, you don't do it with 12 here, you do it with 13. So n equal to n plus 1, we do it like this. 13 divided by 4 is nothing but 3 again. So same calculation goes here and it will be 4, right? Now what you will do is 13 modulo 4 is nothing but 1, right? So what can you do is, there is one value remaining which we don't know whether it is 1 or 0, right? We don't know. So what we will do, we know that for even numbers only it will be 1. So find the current group number, the last group number. What it is? 3. From here also it is 3, right? So the last group number is 3. There is 1, 2, 3. What is the next group number? 4. What is that? Even. So we have to count it, right? Last one is 1, confirmed. So what I can say is, if this is odd, the next one will be even. So the current one is odd, we have to count the remainder set bits, right? So you can say 4 plus remaining is 1 value, that is 5. So totally I got 5 values, that is 5 set bits. Maybe you can take one more thing, maybe 14, until 14 you take it. So let's take n equal to n plus 1, right? So let's take it as 15. 15 divided by 4, how much it is? 4 3s are 12, right? So again 3 divided by 2 is 1, 1 star 4, 4 set bits. We got 3 groups again, right? So this is incomplete, right? This is a complete group. So we got only 3 groups again. Now 15 modulo 4 is 3, right? So what is this? Odd value. Next is even. So if it is odd value, we have to count the remainder also. So 4 plus 3, 4 comes here, 3 comes from here, 4 plus 3 is 5, 6, 7, right? So 7 is a set bit. So if you count here, these are 4, okay, and these are 3. 4 plus 3 is 7. That's how we calculate the set bits for one position. We have to do this process for all positions, right? So what do? We can write the code now. We have to do n equal to n plus 1 first, then we'll do an while loop until we have to check, right? We have to check each position, 2 power 0, 2 power 1, 2 power 2 square, 2 cube, until which power we need to check, until the n numbers we need to check. So power of 2 power I is less than or equal to n. We need to check until this number, right? So again, if this is the first position, like I equal to 0 is the first position, right? First position, right? Now I equal to 0. For 0, it is 2 power 0 equal to 1, right? So first calculate that. Okay, an integer value, fill power of 2 comma I. So this is nothing but 1, right? So like maybe I can take k fill, something like that, because I took here it as k, right? So I can take k fill, or you can just take k instead of fill. Just take k. This is the k value, right? And what I have to do again? We need to find the groups. Integer groups. How do we find the groups? It's very easy. We need to divide n value with the k value, right? So we need to divide the n value with k value. This is the number of groups, right? So, and again, the number of ones. How can I find it? It's very easy. Groups divided by 2 star. What is the number of ones? It's nothing but the k value, right? You do this, right? 1 star 4. This is the same thing I'm doing it here, right? And then what we have to do? We have to find the remaining values. So we already found these values here, these values, but we are yet to find the remaining values here, the uncompleted group, right? So for that we need to find the remainder. Find the remainder. What is the remainder? Int remainder equal to. How do you find the remainder first? N modulo k, right? N modulo k is the remainder. So I need to find something is odd or not. This value, that is n divided by k. That is the group value. If group values is even, so if it is odd, what do you have to do? If it is odd, then only you count it, right? Yes. So if it is odd is group modulo 2. If it is divided by 2, it is even. So what I need the odd number. So is equal to 1. What happens? This is the odd number. Then I have to add the ones. These are ones. So ones plus is equal to, need to add the value. There is the remainder. I need to add the remainder values, right? But maybe I will assign your total ones here 0, and I will add total ones plus is equal to ones, right? This is for only one position. I need to do it for I plus plus every position until n, and return total ones, right? This is a solution for this. So what is the time complexity? As we said, it is log n. Space complexity will be O of 1. We didn't use any arrays, right? So that's how simple it is. Now the next problem. Eighth problem is to set the rightmost unset bit. Okay. So they are giving a number like 6, maybe 0, 1, 1, 0. So the rightmost unset bit is nothing but the first position bit, right? We need to convert it into the 1. That's it. So I just take a while loop until let's say I'll take p equal to n. Let's say n equal to 6, right? And I'll do like this. I'll find the position, right? So maybe I equal to 0. From first position we have to do this. P right shift of I is 1. If it is 1, then we'll do I plus plus, right? Until the ith position is 0, this loop will continue, right? So for I equal to 0, this will not go inside. So we'll get the position I, which is the first rightmost unset bit, right? So what we'll do with this? We have to set, right? So what can I do is n equal to, I need to go to that position, ith position. So how do I go to the ith position? This is the index value, guys. So I just do 1 left shift with I, right? And I set this bit. Set. How do you set the bit? Yes, got it. N or. We just do the or value, right? And return n. That's it. That's how you set the rightmost unset bit. Again, the time complexity is big O of log n. Space complexity is big O of 1. Right? So the next problem is swap two numbers. Swap two numbers. You would say this is an easy problem, right? But you should not use plus operator, minus operator, or any extra variable. How do you do this? If a equal to 13, b equal to 9, how do you do this? Yeah, this should be kind of tricky one. because if you use plus or minus, maybe you can do this, right? I hope you know this. If a equal to a plus b equal to a minus b, a equal to a minus b. If you do this, you'll get the answer easily. With this will swap the two numbers easily, right? But we are not using plus or minus or extra variable. How do you do this? Simple, guys. Just replace plus or minus with XOR operator. A equal to a XOR b equal to a XOR b equal to a equal to a XOR b. This will does this. So how did you find this formula? That's the question, right? So let's say a contains 13, b contains 9, right? I know 13 XOR 9 gives one number, maybe n, right? What is the first step? I'm storing 13 XOR 9, that is n value in a, right? N value. Now what? B equal to a XOR b. So what happens if I XOR 9 with n? What do you think will happen? Yeah, I will get the third value, that is 13. Don't believe me? Just take a couple of numbers and try yourself. 3 XOR 4. We know it is 7 already, right? So 0, 1, 1, 1, it is 7. And 0, 1, 0, 0, it is 4. What is this? Let's do XOR. Different. 1, 1, 0, 0. You see, this is 3. That's how it is. That's how it works, right? Now, this is 13. So instead of 9, it becomes 13, right? And a equal to a XOR b again. So what happens if I do n XOR 13? Yes, you are correct. It will be 9. So instead of this 9, I will be keeping 9. So these things are swapped easily, right? This takes time complexity of big O of 1. This complexity of big O of 1 again. It's very simple problem, guys. Now let's take the 10th problem. That is, you have to divide two integers without using multiplication, division, or the mod operator, right? Without using these three, you have to return coefficient. You have to return the coefficient after dividing these two integers, right? How do you do this? Let's take two examples. One example first. Dividend equal to 22. Divisor equal to 3. Right? Right, guys? Or let's take some bigger example. Dividend equal to 43. Dividend equal to 8. Okay. Now what we have to do? Maybe you can think how to do minus, 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 and I will find the value, right? How many times it will get subtracted, that many times I can do this, right? But this will take more time if this value is near to int max, right? It will take approximately big O of n time. We don't need that. We need the solution in big log of n, time complexity, right? How do you do this? Now let's say 8 is there, right? So what if I left shift this 8 one time? What happens? 8, 4, 2, 1 and 16, 32. Let's say 1, 0, 0, 0 is a bit system for 8. If I left shift 1 by 1, it becomes 1, 0, 0, 0, 0. It becomes 16, right? So maybe let's do it like this. For I equal to 1, for I equal to 1, you have to shift it one time, right? Or we can start from I equal to 0. First we will not shift it. Let's take 43 here and 8 and I equal to 0. So 43 is still greater than 8, right? And let's take I equal to 1, it is 16. Still 43 is greater than 16. Let's take I equal to 2. This will be 32, right? Still 43 is greater than 32. Let's take I equal to 3. This will be 64. Now if you see, the 43 is less than 64. Now I go one step back. I say I will subtract this value. So instead of subtracting 8 directly this many times, big of n times, I will subtract the larger chunk values. Larger chunk values. Right? So subtract larger chunk values to eliminate the number and find the quotient quickly. Now I know 8 into 4 is equal to 32. Right? What is 4 here? 2 square. Right? How I is related to here? You know this. 8 into 2 power I. 8 into 2 power I. Right? So 4 is the quotient here. Right? So 43 minus 32. What is it? 11. Right? So let's keep 4 is our quotient for now. Right? And let's start from I equal to 0 again. And again I will take 8. 11 is greater than 8. Right? I will take I equal to 1. It is 16. Now you see 11 is less than 16. Now I go one step back. So what happens? 8 into 1 equal to 8. This is 2 power 0. That is nothing but 2 power I. So I'll take 1. That is 2 power I is 1. As one more coefficient. Now I do 11 minus 8. I will eliminate the larger chunk values. Right? I'm eliminating 8 now. Instead of previously I did 32. Now 8. What happens? 3. Right? Now compare with 3 and 8. When I equal to 0, you see this is lesser value. 3 is less value than 8. So this is the final remainder. So what can I say here is, when it is like this, I equal to 0 and this is a smaller value, you can go back, right? So you stop it here. Stop it here. Now you find 4 and 1 as two coefficients, right? So add up these two coefficients, that is 5. 8 into 5 is 40, right? This is the original coefficient we need. So return this coefficient value. That's how you solve it. Now there are some edge cases we need to take care of. Right? So what if the dividend equal to int minimum and divisor equal to minus 1. You see this is minus 2 power 31. Right? And this is minus 1. If you divide it by dividend by divisor, it will be 2 power 31. But you know that 32 bits will hold only minus 2 power 31 to 2 power 31 minus 1. Right? So this will overflow the 32 bits number. What we have to do? Yes, what we have to do? We take the long and we just have an edge condition for this, saying if the dividend equal to int min and divisor equal to minus 1, return int max. Right? Int max is nothing but 2 power 31. Right? It cannot be shown in integer value. Now after that, what we have to do? Now again, if we see 43, 8, we got quotient as 5. What if it is minus 43 or minus 8? What happens? It gives rise to minus 5. Right? The coefficient will be minus 5. So we need to find the sign and convert them to their obsolete forms and find the coefficient, and according to the sign we will return the coefficient with the sign value plus or minus. Right? That seems good, right? So first I will take the sign value here. So how do I take it? So plus plus, it is plus, minus plus, it is minus, plus minus, it is minus, minus minus, it is plus. So what do you see here? Yes, you see the XOR operator here, right? It is same, it is plus. It is different, it is minus. It is same, again it is plus. So plus is nothing but our 0 and minus is nothing but our 1, right? So let me take the boolean value. Sign is equal to dividend is less than 0. That is boolean value. 1 or 0, we can say like that in the form of numbers. Divisor is less than 0. So take the XOR value only, right? So if it is less than 0, it will be true. That is negative is 1, right? And positive is 0. That's how we convert this to our sign value. If it is negative, it will be 1. If it is positive, it will be 0. Okay. Finally, we can use of this sign value. Now we need to convert the dividend and divisor to absolute formats. This is a long, right? Let's take long of dividend, long absolute value of b again, absolute value of divisor, right? Now let's store the coefficient q here, right? What do you have to do? Now you see what we have done. We went from here, if you observe 43 and 8, we went from a equal 0, a equal 1, a equal 2, a equal 3, right? And then we go to a equal 0 again, a equal 1, again a equal to 0, and we are changing the a value. We are not changing the b value every time, right? We are changing the a value every time whenever we reach the value that is greater than a value, right? Let's say I will iterate until I'm changing the a value, right? So I will iterate until a is greater than or equal to b. If 3 is less than 8, then only we stopped it, right? So until a is greater than or equal to b, we continue it, right? That's how it happens. We start with I equal to 0 every time, right? You see here, I equal to 0, I equal to 1, I equal to 2, I equal to 3. Now after changing a, we are starting from I equal to 0 again, I equal to 1. After changing a, we are starting with 0 again, right? So let's do this. We have to start from 0. We take a while loop again. We go until I is less than 31, right? We go until 30. And what we have to do? We are left shifting it by I, right? Let's do it. So b left shift of I is less than or equal to a. Then continue incrementing I, right? Until it's no longer less than a, right? So if 43 is greater than 64, then we stopped it and went back to 32, right? So what we have to do? By the time we come here, I is 3. I is 3. By the time we came here, but we need I equal to 2. So we do I minus here, and we subtract the shifted value for b, right? Like 43 minus 32, how we did it. This is what we are doing here, right? And we add the coefficient here, right? The 4 value, this is 2 power I, we have to add 2 power I, right? 2 power I, how do we do it? We can use power of 2 comma I. Yes, we can do like this, 1 left shift by I, right? This is the 2 power I, 1 left shift by I, like this, 2 power 0, 2 power 1. So 1 will be here first time, left shift by 1, it will go to 2 power 1, right? That's how it works. And then close the while loop. Now you have to return the coefficient, right? But wait, we need sign also here. So if sign is 1, then it is a negative value, right? Minus q, else it is normal. So this is a code for finding the coefficient without using multiplication, division, or modulo operator, right? The time complexity will be big O of log n again. Space complexity will be big O of 1 again, right? Now the next problem is, the 11th problem is power set. Power set. So what is this power set? It is also very simple, guys. For s equal to a, b, c, this is a string. I get all the subsequences in lexicographically. So you forgot about the lexicographically, right? What about subsequences? Subsequences are nothing but, let's say I start from a. I start with a. This is a subsequence, and I will add b, ab. This is a subsequence, and I will add c, A, B, C. This is a subsequence. Now I will start with B. B. This is a subsequence. And I will add C. B, C. This is a subsequence. And I will start from C again. C. This is a subsequence and that's end here. So I got all these 1, 2, 3, 4, 5, 6. 6 subsequences. Right? Like this. So these are subsequences I found for ABC. But if we have to find these subsequences, we need to take 2 for loops. We go of n square, right? We need to start from A until n and B until n. So we do it n times. N into n equal to n square, right? Now to get the power set, what we have to do? For A, what we are doing? A, B, C. We are taking A, not taking B and C, right? For AB, what we are doing? We are taking A, B, not taking C. And for A, B, C, what we are doing? We are taking all of them. And for B, what we are doing? 0, 1, 0, because we are taking B, right? For DC, what we are doing? 0, 1, 1. And for C, what we are doing? We are not taking A, we are not taking B, we are taking C. So if you observe this, these are the numbers, right? 4, 2, 1, let's calculate. This is 4, this is 6, this is 7, this is 2, this is 3, this is 1. So if you observe, there will be all numbers from 1 to 7, right? If you not take anything, 0, 0, 0, that is 0. So you can tell 0 to 7, right? So what is this? 0 to 2 power 3 minus 1. You see A, B, C is of length of 3, right? If you observe here, 0 to 2 power length minus 1. So these many times we have to take these strings, right? What we can do is, if we iterate through this each number, and for each number we'll take the each position bit value. If it is 1, then we'll take it. If it is not 1, we'll not take it, right? So what can we do is, we'll take the n value first. N is nothing but the size, s dot size, okay? Then we'll take the vector of strings, right? Answer. Let me store the empty value here. This also counts. Now we'll start from either n equal to number equal to 0 or 1. Anything is fine, and we will go until 2 power length minus 1, right? So 2 power length is nothing but, we can write it like this. Length is 2 power n, right? So we can write it like this: 1 left shift of n, right? So we'll go until 1 left shift n minus 1. So we can write like this: 1 left shift of n. So and number plus. Now we'll create a string here, temporary string, v subsequence. For every position, so there will be how many positions? If you observe here, length is 3, we have 3 positions, right? Every time. So I can take n here. That's why I took n here, right? Now if the value of that number at that position, I can take the position value, I can send 1 to that position, and I check if it is 1 or not. If it is 1, then what I have to do? I will add this to our subsequences, right? Now after this for loop is done, we'll have our subsequences ready. I will push that subsequence to our answer, right? Like this. Now our answer will contain all the subsequences here, right? But here is the twist. They said lexicographically sorted order. So it's very simple. Just sort it. Sort the array. Sort. In C++ we do it like this. Sort answer dot begin, answer dot end. So it will sort the elements in lexicographical order, then return answer, right? So this answer will contain all the subsequences now. So this is nothing but the power set, right? That's how we calculate the power set of any string using bit manipulation, right? If you like this video, please share and subscribe and comment down you need more videos like this. It will motivate me to make such kind of videos. Thanks for watching.